Okay, we're going to talk a little bit more about curve fitting. So let me remind you what we did last time. So what we talked about was we were given a set of data points, T1, Y1 through Tm, Ym, and those are plotted in this graph. And we're looking for the best line, y equals alpha x plus beta, to fit the data. And all we need to do is find alpha and beta. And we did a little bit of linear algebra to conclude that if we set A to be this matrix here, and then K to be A transpose A, which is a 2 by 2 matrix, and then we do this calculation, K inverse A transpose Y, that gives me alpha and beta. So I did that in the video last time. We did an example in class, and there will be some in your homework. Let me make a couple of comments about this and then go on to a generalization. So if you look in the book, there's actually, it's possible to work this out in general, basically skip all of the linear algebra and just give the answer. And the answer is the following, that beta has the following expression, summation Ti minus T bar times Yi over Ti minus T bar squared. This is the sum, where these sums are all from Y to M, and the bar means average. So T bar is the average of all of the T's. And alpha then turns out to be Y bar minus T bar beta. So the slope is beta. That's the most complicated thing. That's given by this expression. And alpha is calculated from the slope like this. You need, oh, sorry, there's a bar over here. You need the average of the T's and the average of the Y's and this beta that you just computed. Okay, so I just want to remind you where this formula came from, because it's actually pretty easy, and the basic idea, it's worth remembering. So how do you figure out this alpha beta for the curve fit? Well, the basic idea is that you try and solve the equation yi is equal to alpha plus beta ti for all these different i's, 1 through m. If you could do that, then the line would go through all of the points. Well, you might not be able to do that, but we'll come as close as we can. And then you just make the simple observation that you can rewrite this equation as y is equal to a times alpha beta, which is to say 1, 1, 1, dot, 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 T1, T2, dot, 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 times alpha beta. This set of equations, as I runs from 1 to m, is exactly the same thing as this matrix equation, y is equal to a times alpha beta. And then you just solve this, or do the least squares solve solution. And how do you do that? Well, you need to make A symmetric, so you multiply both sides by A transpose. And we're trying to solve this equation. And if you can solve it exactly, you have a line that goes through all the points. But the best fit is now just this formula, K inverse F, in the terminology that we've been using before, which is to say K inverse, where K is this matrix A transpose A, and F is this thing over here, A transpose Y. And that's all there is to it. That's the pretty much a complete derivation of that formula. And the key step is this one right here, is recognizing that you can write this collection of equalities as a single vector equation like this. Okay, well, let's go on and let's generalize this. Instead of, well, suppose I have some data like before, T1 through TMYM, and what I just did is I tried to find the best fit by a line at y is equal to alpha plus beta x. Well, why did I stop there? Why not try and fit it with a quadratic, like a parabola? Y is equal to alpha plus beta x plus gamma x squared. This gives me more freedom and possibly a much better fit. So if you have a bunch of data which looks more like it's fit by a quadratic function, this will find the best parabola to fit that data. And well, part of the reason I reiterated what I said on the previous page is because now we're almost done here. We just have to we just have this one extra term. So this vector that we're interested in is a 3-vector, alpha, beta, gamma. And the only change now is that you take A to be, before we took it to be 1, and then T1 down to Tn. And now you put in a new T1 squared down to Tn squared. Okay, that's the new ingredient in this case. And what's the idea? Well, just like before, if we actually wanted to fit a parabola exactly to this equation, we would try and solve yi is equal to alpha plus beta ti plus gamma ti squared for I running through 1 to m. And that just becomes the matrix equation y is equal to A times alpha, beta, gamma. And this gamma term here is going to get multiplied by the last column here. And that's giving you your gamma x squared and gamma ti squared terms. So it's very much like what we did before. It's just you have an extra column in the A matrix and an extra factor in this matrix alpha, beta, gamma. And the rest of it's exactly the same. And so the solution is given by alpha, beta, gamma is equal to A. Let me write it like this. It's equal to K inverse A transpose Y. Exact same formula, and where K is exactly as before. K is A transpose A. Well, it's pretty obvious what the general formula is now. If you are trying to fit a bunch of data, T1, Y1, ... and you're trying to fit it with a curve of the form alpha 0 plus alpha 1 x plus alpha 2 x squared plus ... alpha r x to the r, for any r, the matrix that you use is A. Looks like this. You put 1s in the first column, and then and then you put T1, T2 down to Tm, followed by T1 squared, T2 squared, down to Tm squared, and finally you get up to T1 to the r, T2 to the r, down to Tm to the r. Pretty interesting, huh? So this, what size is this? This is an M by r plus 1 matrix. And the vector that we're looking for, this target vector, is alpha 1, alpha 2, up to alpha r, starting with alpha 0, which is an r plus 1 vector. And again, the best fit is given by this vector alpha is equal to A transpose A inverse times A transpose Y. So let's think a little bit about this some more. So remember, we're given points T1, Y1 through Tm, Ym, and we're also specifying the degree of the polynomial we're interested in. Y is alpha 0 plus alpha 1 x plus dot 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 alpha r x to the r. And what we get out of this is this matrix A, which is of size m by r plus 1. And it's particularly interesting to consider the following case. What if this matrix is square? What if m is equal to r plus 1? So what does that mean? It means that I'm given m points, and I'm trying to find a polynomial of degree r, which is to say m minus 1, which fits it. So let's make a little table here. We started with, let's see, we want to start with m is equal to 2 and r is equal to 1. And then m goes up from there, m 2, 3, 4, r is equal to 2, 3, and so on. So let's look at these cases one by one. What does this case mean? M is the number of points. So I'm given 2 points, and I'm trying to find the best fit by a polynomial of degree 1, which is to say the best fit of a line which goes through those 2 points. Well, you can get a perfect fit. If given any 2 points, I hope I don't need to remind you, there's a line through them. Okay, what about this case? So here I'm given 3 points, and I'm trying to find a quadratic which fits a plus bx plus cx squared. Well, that case also, you can also fit exactly. If you're given any 3 points, you can find a parabola which goes through them, and so on and so forth. So in the special case when m is equal to r plus 1, then you can fit exactly, which is to say the error is 0, and you can solve the equation exactly. So let's think a little bit about what that means. So we're talking about the case m is equal to r plus 1. And we're being given m points, and we're trying to fit that with a polynomial of degree r, which is to say m minus 1. So, for example, 2 points with a line, or 3 points with a quadratic. And the matrix that comes up is this square matrix, 1, T1 down to T m, up to r is equal to m, anyway, it's T 1 to the m minus 1 dot 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 T m to the m minus 1. This is the matrix which comes up. And let me remind you, this is an m by m matrix. So the powers here go 0, 1 up to m minus 1, and there's m rows. And I'm saying that this equation, remember what we're trying to solve is A and remember what we're trying to solve is the equation A alpha is equal to y, where y are the y values and alpha is this coefficient, the coefficients that we're looking for, like that. And so here we are in a fairly comfortable, familiar situation. This is an m by m matrix, and these are all m vectors, and I'm trying to solve an equation in Rm. And I'm saying that it has, I said on the previous screen, this has an exact solution. Well, the only way that can be is if A is invertible. Because then if A is invertible, you can simply take alpha is A inverse y. So is this matrix invertible? Looks pretty complicated. Well, it depends on the t's. Obviously, if T1 is equal to T2, it can't be invertible because, put the T2 in here. If T1 is equal to T2, then the two rows are the same. And so the determinant is equal to 0. But it's a quite a nice theorem that if the Ti is never equal to Tj, if all the Ti's are distinct, then the determinant of A is not 0. And this A is called the Vandermonde Matrix. And it's quite a famous matrix. It comes up lots of places, and in solving simultaneous equations, it's very common that this arises. And maybe I'll say something in class about why this is true, but it is true. The determinant is non-zero. And let me just say one or two more things about this. So what I just said was we're trying to solve the equation A alpha is equal to y, which I solved by setting alpha equal to A inverse y. But that's not what I got before. If I use the formula from before, what did I say? The general case was I get that alpha is equal to A transpose A inverse A transpose y. That's what the general method gives you. This is our k, and so on. And is that the same thing as this? Well, of course, it is. You just notice that A transpose A inverse, this is just saying that this is equal to A inverse A transpose inverse A transpose y. Because when you take the inverse, you switch the order. And then these two terms cancel, and you get A inverse y. So all is right with the world. Well, let me just conclude with a question. What I just did makes me ask the following. Suppose M and R are not necessarily the same. So I have MR, and I have this equation AX is equal to Y. And I use the best fit method that I was just talking about, and I get that the best fit is X is equal to A transpose A inverse A transpose Y. Okay, I'm just repeating myself over and over again. That's the formula we've been using. Now, my question is, why can't I just do the following? Right, this says A inverse A transpose inverse A transpose Y, and that's equal to, after I cancel these, A inverse Y. Sorry for the garish colors. I should erase that and do it in red. I get A inverse Y. Well, why not? Are these the same? And if so, why did I give this more complicated formula when this works? And I'll let you think about that, and we'll talk about that in class.